Welcome to Fascinating Facts. Have you ever looked up at the night sky filled with its countless stars and wondered where it all came from? Where we all came from? Today, we're diving into the most epic origin story ever told, the Big Bang Theory. This isn't just some abstract scientific idea, it's the very foundation of our reality. It's the story of how everything we know and everything we are, space, time, matter, and energy, burst into existence from a single, infinitesimally small point. It's a story that connects every atom in your body to the farthest reaches of the cosmos. From the tiniest subatomic particles dancing in the quantum foam to the grand, spiraling galaxies that stretch across billions of light years, all of it, every single bit, began with one unimaginable, cataclysmic event some 13.8 billion years ago. This theory isn't just a guess. It's a monumental achievement of human curiosity, built upon decades of observation, mathematics, and relentless questioning. It's our best scientific explanation for the birth of the universe. So get ready to have your mind expanded. Forget what you think you know, and prepare to journey back to the very beginning of time itself. Together, we'll explore 15 fascinating, mind-blowing facts about how it all started. We'll peel back the layers of cosmic history to witness the birth of everything. Let's begin our journey to the dawn of creation. Our story begins not with a bang, but with a point, a singularity. Imagine all the matter and energy of the entire observable universe, every star, every planet, every black hole, every particle, compressed into a region of space smaller than a single atom. This state of infinite density and temperature is where our cosmic timeline begins. It's a concept that pushes the very limits of our imagination and even our physics. At this moment, the laws of nature as we know them break down. There was no before in the way we understand it. From this single, intensely hot and dense point, the universe didn't explode into an existing void. Instead, space itself began to expand, carrying all that energy and matter with it. Think of it like the surface of a balloon being inflated. As the balloon expands, the points on its surface move farther apart, but there's no center to the expansion on the surface itself. This expansion, which started 13.8 billion years ago, is the very fabric of our cosmic evolution, a process that continues to this day, shaping the grand tapestry of the cosmos. So, what happened before the Big Bang? It's a question that has tantalized philosophers and scientists for ages. But according to our current understanding, the question itself might be meaningless. According to Einstein's general theory of relativity, space and time are interwoven into a single continuum space-time. The Big Bang wasn't just the beginning of matter and energy, it was the beginning of space-time itself. Time, as a dimension, was born in that initial moment of creation. Think of it this way. Asking what's north of the North Pole is a nonsensical question. Once you are at the North Pole, every direction you can possibly go is south. There is no north of the North Pole. Similarly, in the context of the Big Bang, there was no before for time to exist in. The singularity represents the 0 point of our cosmic timeline. It's the ultimate starting line from which the entire history of the universe and time itself began to unfold second by second, eon by eon. For much of human history, we believed the universe was static, eternal, and unchanging, a perfect clockwork cosmos. That comforting idea was shattered in the 1920s by the work of astronomer Edwin Hubble. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble observed that distant galaxies weren't just sitting there. They were all moving away from us, and the farther away they were, the faster they were receding. This was a revolutionary discovery. This observation, now known as Hubble's law, provided the first major piece of evidence for the Big Bang. If everything is moving apart now, it stands to reason that in the past, everything must have been much closer together. By rewinding this cosmic expansion, we arrive back at that initial super-dense state. Hubble's discovery transformed the Big Bang from a fringe hypothesis into the leading theory of cosmology. It painted a new picture of the universe, not as a static portrait, but as a dynamic, evolving, and ever-expanding masterpiece. If the universe began in an incredibly hot, dense state, there should be some leftover heat, a faint afterglow from that primordial fire. For decades, this was a key prediction of the Big Bang theory, but it remained undiscovered. Then, in 1965, two American radio astronomers, Arno Penzias and Robert Wilson, stumbled upon it by accident. They were trying to eliminate a persistent faint hiss in their radio antenna, a noise that seemed to come from every direction in the sky, day and night, no matter where they pointed it. What they had found wasn't equipment malfunction or pigeon droppings, as they initially suspected. It was the cosmic microwave background, or CMB. This is the residual heat from the Big Bang, a faint glow of microwave radiation that permeates all of space. It's the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. Finding the CMB was like finding the fossilized echo of creation itself, confirming the Big Bang in the most profound way and earning Penzias and Wilson the Nobel Prize. The universe cooled as it expanded, but this cooling process wasn't instantaneous. For the first 380,000 years, the universe was a scorching, opaque fog of plasma. It was so hot that electrons couldn't be captured by atomic nuclei to form stable, neutral atoms. Photons, particles of light, were constantly scattering off free-floating electrons, trapped like a car's headlights in a dense fog. Light couldn't travel freely, so the universe was dark, not in the sense of no light, but in the sense of being completely opaque. Then the universe reached a critical tipping point. It cooled to about 3,000 Kelvin, cool enough for protons and electrons to finally combine and form the first neutral hydrogen atoms. This event is known as recombination. Suddenly, with the electrons locked into atoms, the photons were set free, the cosmic fog lifted, and the universe became transparent for the very first time. The light from that moment is what we see today as the cosmic microwave background. It's the universe's baby picture, the first light ever to travel unimpeded across the cosmos. In the very first moments after the Big Bang, the universe was a chaotic soup of fundamental particles and radiation, far too hot for even protons and neutrons to form. But as it expanded and cooled, a crucial phase began. Between about 1 second and 3 minutes after the Big Bang, the universe cooled enough for protons and neutrons to fuse together, forming the first atomic nuclei. This process is called Big Bang nucleosynthesis. It was a frantic cosmic alchemy that lasted for only a few minutes. In this brief window, the universe forged nearly all of the hydrogen and helium that exists today, along with trace amounts of lithium. Essentially, the entire universe acted as a single massive fusion reactor. The abundance of these light elements we observe in the cosmos today, about 75% hydrogen and 25% helium by mass, perfectly matches the predictions of Big Bang nucleosynthesis, providing another powerful pillar of evidence for our cosmic origin story. The standard Big Bang model explains a lot, but it left a few cosmic puzzles, like why the universe is so remarkably uniform and flat on large scales. The solution is a mind-bending concept called inflation. According to this idea, in the first fraction of a second after the Big Bang, from about 10 to the minus 36 to 10 to the minus 32 seconds, the universe underwent a period of astonishing exponential expansion. It grew from smaller than an atom to larger than a grapefruit almost instantaneously. This hyper-expansion smoothed out any initial wrinkles or irregularities in the fabric of spacetime, just as inflating a crumpled balloon makes its surface smooth. It stretched tiny quantum fluctuations to enormous scales, which later became the seeds for the large-scale structures we see today, like galaxies and galaxy clusters. While a direct observation of inflation is still beyond our grasp, its predictions align perfectly with the detailed maps of the cosmic microwave background, making it an essential ingredient in our modern understanding of the Big Bang. We call it the Big Bang, a name that conjures images of a colossal explosion, a deafening cosmic roar. The name, originally coined as a term of derision by astronomer Fred Hoyle, is actually quite misleading. The Big Bang wasn't an explosion in space, it was the expansion of space itself, and it was completely, utterly silent. Why? Because sound needs a medium to travel through. Sound waves are pressure waves that propagate through a substance like air or water by causing its molecules to vibrate and bump into each other. In the nascent universe, there was no air, no medium for sound to travel through. The bang was the rapid inflation of space-time itself, a silent, unfolding process. So while it was the most powerful event in history, it occurred in perfect silence, a silent genesis for the sound-filled world we would one day inhabit. After the universe became transparent, it was still a mostly uniform sea of hydrogen and helium gas, dotted with the tiny density variations seeded by inflation. It was far from the star-filled cosmos we see today. The formation of galaxies was a slow, patient process, governed by the relentless pull of gravity. Over hundreds of millions of years, gravity began to draw matter together in the slightly denser regions of space. These small clumps of matter grew larger and larger, attracting more gas and dust, eventually collapsing under their own weight to form the first stars and small protogalaxies. These early galaxies were small and irregular, but through countless mergers and collisions over billions of years, they grew into the grand spiral and elliptical galaxies we now observe. Our own Milky Way galaxy likely began forming around 13.6 billion years ago, and its majestic spiral structure, including our solar system, took billions more years to assemble. So get this, the ordinary matter we see all around us, like the stuff that makes up stars, planets, and, well, us, only adds up to about 5% of the universe's total mass and energy. A much larger chunk, roughly 27%, is this mysterious, invisible substance called dark matter. Now, we can't actually see dark matter or touch it, but we know it's out there because we can spot its gravitational effects on things we see, like the way galaxies spin. Dark matter was actually super important right from the start. Since it doesn't interact with light, it wasn't shoved around by radiation pressure in the early universe. That meant it could start clumping together way earlier than regular matter, forming these vast, invisible halos. These dark matter halos acted like a kind of cosmic scaffolding, creating gravitational wells that pulled in ordinary gas and dust. Without dark matter, gravity just wouldn't have been strong enough to build galaxies and other huge structures as fast as they did. It's pretty wild, but dark matter is basically the unseen architect of the cosmos. You know, it's totally normal for us humans to want to put ourselves right at the center of everything. For centuries, we actually thought the Earth was smack dab in the middle of the universe. Even now, when people talk about the Big Bang, it's easy to imagine it as some giant explosion happening at a specific spot in an empty room. But honestly, that idea is just wrong. The Big Bang didn't happen at a single point in space. It happened everywhere at once. Since the Big Bang was really the expansion of space itself, every point in the universe is just as good as any other to call the center. From wherever you look, like from any galaxy, all the other distant galaxies seem to be moving away, just like how we see it from the Milky Way. There's no central point where the universe started expanding. And actually, there's no edge either. The universe isn't a sphere blowing up into empty space. The universe, the thing that's expanding. We're all part of that expansion together. So, the Big Bang gives us the story of how everything started, but what about how it all ends? That's honestly one of the biggest mysteries in cosmology, and it all comes down to this cosmic tug-of-war between the outward push of expansion and the inward pull of gravity. The answer depends on the overall density of matter and energy in the universe, which scientists call omega. For a long time, people thought there were three main ways things could go. If the universe's density was high enough, meaning omega is greater than 1, gravity would eventually win, stop the expansion, and everything would collapse back together in what's called a big crunch, kind of like a reverse Big Bang. If the density was too low, omega less than 1, expansion would win out, and the universe would just keep expanding forever, getting colder and darker in a big freeze. And if the density was perfectly balanced, omega equals 1, the universe would still expand forever, but the rate would slow down over time, leading to a big chill. So, yeah, the fate of literally everything hangs in this really delicate balance. The Cosmic Fate story got a shocking plot twist in 1998. Two independent teams of astronomers were observing distant supernovae to measure how much the universe's expansion was slowing down. But, they found the exact opposite. The expansion wasn't slowing down at all. It was actually speeding up. The universe is accelerating its expansion, pushing galaxies apart at an ever-increasing rate. This was a discovery that honestly shook the foundations of cosmology. To explain this cosmic acceleration, scientists propose the existence of a new mysterious force or energy that permeates all of space and has a repulsive gravitational effect. They called it dark energy. It makes up a staggering 68% of the universe, and we have almost no idea what it is. This discovery means that our ultimate fate is likely the Big Freeze, but on an accelerated timeline. The universe is destined to become a vast, cold, and lonely place as galaxies accelerate away from each other, eventually disappearing beyond our cosmic horizon. The Big Bang Theory isn't just a clever idea or a wild guess. It's actually a robust scientific theory supported by multiple, independent lines of overwhelming evidence gathered over nearly a century. This convergence of evidence is what gives us such confidence in our cosmic origin story. It's not a matter of faith, it's a matter of observation and data. So let's recap the four main pillars. First, there's the expansion of the universe observed by Hubble, which shows that everything is moving apart. Second, we have the cosmic microwave background, the faint afterglow of the hot, early universe. Third, the observed abundance of light elements, hydrogen and helium, perfectly matches the predictions of Big Bang nucleosynthesis. And fourth, the evolution and distribution of galaxies on large scales fit precisely with a model of a universe that started hot and dense and has been expanding and cooling ever since. The Big Bang Theory marks the beginning of our universe, but it's far from the end of our understanding. In fact, it opens up a whole new realm of profound questions and cosmic mysteries. What is dark matter? What is dark energy? This force that's tearing our universe apart at the seams? What happened in the very first instant of the Big Bang, during the singularity itself, where our current laws of physics fail us? Was our Big Bang the only one? These are the questions that drive cosmology forward today. Scientists around the world are using powerful new telescopes, particle accelerators, and theoretical models to peer deeper into the cosmic darkness and closer to the moment of creation. The quest for knowledge is a journey without a final destination. The Big Bang gives us our context and our history, but the future of our cosmic understanding is still unwritten, waiting for the next generation of curious minds to discover. The greatest adventure is still ahead of us. From an infinitely dense point to the vast, accelerating cosmos we inhabit today, the story of the Big Bang is the ultimate story of transformation. It's a narrative written in the language of physics and observed in the light from distant galaxies. It connects every one of us to the grandest scales of space and time. The journey from that first moment to this one, reading these words, has been 13.8 billion years in the making. Every discovery, from the expansion of space to the echo of creation, only deepens our sense of awe and our place within this cosmic drama. The universe is not something separate from us. We are a way for the cosmos to know itself. The iron in your blood, the calcium in your bones, the oxygen you breathe, these elements were forged in the hearts of dying stars, which themselves were born from the hydrogen and helium created in the Big Bang. So when you look up at the night sky, remember, the universe isn't just out there, it's part of you. After all, you are made of star stuff that began in the Big Bang. Thank you for joining us on this journey through space and time. If you found these facts as fascinating as we do, please support our channel. Follow fascinating facts like this video, share it with a fellow explorer, and let us know your most mind-blowing thought in the comments below. Stay connected and grow every day with fascinating facts. Thanks for watching.